And now we're going to embark upon some fairly recent exam questions from the AQA syllabus about heat capacity, or specific heat capacity. I'll pause every now and again and check mark scheme to make sure I'm getting the right answers for you here. But first of all, we've got a real world example here, an electric kettle used to boil water. And what they've said here, they've used it to heat up water, and after boiling, the temperature has dropped by 22 degrees C. So going back to our heat capacity equation, the energy transfer is the mass multiplied by the heat capacity multiplied by the temperature change, theta. So energy is mc theta. All right. So what we've got here is that its temperatures dropped by 22 degrees C. The mass of the water was 0.50 kilograms, and the heat capacity was 4,200. So easy, quick substitution question. E is the mass involved, 0.50 kgs. Don't forget the O's, they're important. And the heat capacity, 4,200. And the temperature drop, which is 22 degrees C. They've asked us the energy transferred to the surroundings, so I won't bother with minuses and stuff here. Right, work out those numbers very quickly. So 0.5 multiplied by 4,200 multiplied by 22 degrees C change, and we get 46,200 joules. Right, now I could leave that as 46,200. If I want to be pedantic, I could say each of these are just two significant figures. So I could, if I wanted, round that to 46,000 joules. I will find out in a second what they've said. Yep, either answer acceptable, 46,200, or indeed rounding it to 46,000. So those are both okay. Right, moving on. Right, why is the total energy input to the kettle higher than the energy used to heat the water? It's because whilst you're heating up the water from 0 to 100, from room temperature to 100, you've also got to heat up the kettle itself. So the stretch of the kettle's got to be heated up, and this will be therefore the box that you've got to tick. That's wrong, because when the kettle's warmer than the surroundings, it's not going to absorb heat from it, and more than 100% efficient, that's just not possible. Right, then we've got a cyclist riding along a flat road. Okay, we've gone into a little bit of your forces topic here, which you'll come across, but as a cyclist accelerates, it's the store that's in his body, which is going to be chemical, decreases. He uses up chemical energy, and he's making himself go faster, so his kinetic energy is increasing. So that's some stuff from elsewhere in the energy topic. Right, he's using up his energy, transferring it to movement, off he goes. Right, now they've told us the cyclist is that mass, and he's this meters per second. Again, from the rest of the energy topic, they've even given you the formula here. Figure out the kinetic energy. Right, half the mass multiplied by the speed. So it's going to be 80 kgs multiplied by his speed squared, I should have said, multiplied by 12, and if you like, by 12 again, and then divide the whole lot by 2. All right, you can put it in as the squared if you like. That's perfectly okay. So 80 multiplied by 12 squared, and then divide the whole lot by 2. And you're going to get 5760 joules from that. Right, quick check. Yep, that is indeed what we're expected to get. 5760 joules. They've given us the units, so I'm going to worry about that. Now, this is the bit that's involving heat capacity. Brakes transfer kinetic energy into thermal energy. That's how they work. They get very hot. So the temperature of the brakes increases by 50 degrees. The mass of the brake pads is 0.040 kilograms, and the heat capacity of the material of the brake pads is 480 joules per kilogram per degree C. That's interesting. Okay. Right. And so we're going to have here change in the thermal energy of the brake pads using this equation. So it's just using our standard one, energy change mass times SHC times temperature change. So put in the numbers, 0.040 kgs. Heat capacity, they've told us, 480. Temperature rise, 50. Right, the numbers for which will come out as 0.040 multiplied by 480 multiplied by 50. Right. And we get 960 joules from that. Again, I'll check we got it right. Yes, indeed, 960 joules is the answer. And then internal energy, as you'll come across, internal energy, that is sort of our official word that we use for heat or thermal energy. It's because if you're talking about the strict term of internal energy, it means all of the thermal energy of the particles in the brake pads, that is their energy due to how the little particles are moving around, but it also includes their potential energy because they're bouncing back and forth on their bonds, and the bonds are storing some energy as well. So the total internal energy stored is called the internal energy, and that actually includes the potential energy in the bonds as well from being bounced about. But just so it's really, if you want to, in simple terms, it's how does the heat energy of the particles, how is it affected by the increase in temperature? Well, surprise, surprise, their internal energy, their thermal and their PE as well, is increasing. So that one's straight, that one's done. Now we'll move on, and we have got a coffee machine. Fancy. Right, it uses an electric element, electric heater, that's what they mean. Those heating things are called heating elements, and heats up the water inside it. It has a metal case as well. Right, this is something from your electricity topic, which you will do next year. Live wire, if it touched the metal case, you could cause electrocution, because it would mean that a person who touched the outside of the kettle could get electrocuted, could get an electric shock for the user. Okay, right, I'll move on from that. You'll do that in electricity next year. Now, this is something we're going to do stuff about as we're doing this energy topic, and as you may touch upon in your forces topic next year. Power, right, is for all things, it's energy divided by time, but it's also for electricity. Power is PD, or voltage, multiplied by current. So it's V times I, using the symbols for electricity and current. Now they've given you here a power in kilowatts. They've given you a PD of 230. Work out the current. Okay, well, we've got that power is V times I. Rearrange that. Current is going to be power divided by PD. So the power is 2.3 kilowatts. It's 2.53 kilowatts. So you can write that as 253 watts. The PD 230, put those two together, 2530 divide 230, and we get a current of 11 amps. All right. Just a little bit of exam technique. If you get something like 300 amps, that's rubbish. The biggest fuses you get in anything in your kitchen, anything or any ordinary appliance, the biggest fuse is 13 amps. So if you get a crazily big amps number, you've got something wrong in this calculation. Right, now this is back to our specific heat capacity and a little bit of thinking about the coffee machine has heated some water from 20 degrees to 90 degrees C. So theta, the temperature change, is 90 minus 20. The temperature changes by 70 degrees C. Right. They've given you here a power output of 2.53 kilowatts. Right. And down here they're giving us a time that it's going to be on for. Now, you may recall up here I said that generally power is energy divided by time. So if you've got power is energy divided by time, then energy is power multiplied by time. Right? You'll become more familiar with this as time goes by, but we'll need that to work out our energy. Right, we've got a heat capacity here. So the first bit of this question is watts. We're going to need to work out what the energy transfer is. Right, the energy transfer is the power multiplied by the time. The power is the 2530 watts. The time is 14 seconds. That gives us a power an energy transfer of 2530 multiplied by 14, so 35,420 joules. Right, we need to know that because the next part of the question is working out the mass of water, and here we're using energy is m times c times theta. Rearrange it using the old triangle if you prefer, and then E mc theta. Right, and if you rearrange that, cover up m, you get m equals E divided by c times theta. So we're going to substitute in here. We've got an energy that we worked out, 35,420. Then we've got C for water, 4,200, and a temperature change of 70. Right. This is, by the way, the really hard question at the end. It's pretty much the hard question at the end. Right. Again, you can do this in various ways. You could plug into your calculator that it's 35,420 divided by 4,200 and hit the equals, and then divide by 70 and hit equals again, and you get a mass of 0.120 kgs. Right. The other way of doing it, as I said, multiply those two together, get one number, and then 35,420 divided by that number. I'll also do it the other way with brackets, 435,420 divided by open brackets 4200 multiplied by 70 close brackets equals, and I also get 0.120 kilograms. Checking it in the marking scheme, and indeed that's what they get, 0.120 kilograms. Right, bedeep, but that's all, folks. Right, that last one was a bit of a stinker, but I just thought I'd stick it in because that's showing you a bit of an intro to some of the things we'll do later on. Power and energy you should know about, or you should know a bit about already. But this is all just same old stuff with rearranging your equations for heat capacity and mass and temperature change. Okay, take care everyone.